Hello, so today we will be presenting our metallographic analysis of carburized steel for our engineering materials course. So our focus on this project is on understanding how carburizing changes the microstructure and mechanical behavior of steel. So basically, carburizing is a heat treatment process used to increase the carbon content on the surface of low carbon steel. This process forms a hard wear resistant outer layer while the core remains softer and ductile. Essentially, we get a material that is both strong at the surface and tough inside. The objectives of this project is to evaluate microstructure of the carburized steel specimen, determine the root cause of performance issues, assess mechanical properties of the carburized steel of specimen, and propose testing and failure analysis techniques, and lastly to develop teamwork and problem solving skills. Okay, so for the material overview, the sample is carburized steel. The average composition of the sample is 0.2% carbon and 0.5% manganese. So for the heat treatment, it use liquid carburizing, and for the etchant is nitrile, and the magnification for this project is 100x. So for the working plan, we plan to first use metallography tests on the carburized steel, and then hardness test, and also case depth analysis. So for metallography, we use a STM E3 sample preparation STM, and also E407 microstructure etching. For hardness test, we use a STM E18 standard, which is Rockwell and hardness test, and also STM E92 viscous hardness. And for case depth analysis, we use AS-A255, which is carburized depth measurement.
For the metallography in section 4.1, our goal was to prepare the steel sample so that its microstructure could be clearly observed. We mounted the sample using a bakelite mounting press, then performed sequential grinding using different abrasive papers to obtain a flat and scratch-free surface. After that, we polished the sample to a mirror finish and etched it with a 2% nitrile, which helps reveal the ferrite-ample light phases. Finally, we examined the etched sample under an optical microscope at 100 times magnification and captured the micrographs for analysis.
In this part of the report, I will explain the safety and laboratory procedures that must be followed during metallography, tensile testing, and harness testing. First, personal protective equipment is essential. We must always wear a lab coat to protect against metals, debris, safety goggles to prevent flying particles during grinding or cutting, closed-toe shoes, and specific gloves. Nitrile gloves are used when handling chemicals such as nitrile, and heat-resistant gloves are needed when touching hot samples after cutting or mounting. Chemical safety is also very important. Etching must always be done inside the fume hood because nitrile is corrosive and flammable. Chemical waste must never be thrown in the sink but into the proper containers. In this part of the report, I will explain the safety and laboratory procedures that must be followed during metallography, tensile testing, and harness testing. First, personal protective equipment is essential. We must always wear a lab coat to protect against metals, debris, safety goggles to prevent flying particles during grinding or cutting, closed-toe shoes, and specific gloves. Nitrile gloves are used when handling chemicals such as nitrile, and heat-resistant gloves are needed when touching hot samples after cutting or mounting. Chemical safety is also very important. Etching must always be done inside the fume hood because nitrile is corrosive and flammable. Chemical waste must never be thrown in the sink but into the proper containers.
The main objective was to understand how the carburized steel behaves under axial loading. We first measured the specimen dimension with a vernier caliper and then mounted it on the universal testing machine. During the test, the machine applied a controlled load and recorded the force and elongation in real time. which allowed us to generate the stress strain curve. The carburized steel showed a typical dual behavior. The hardened surface increased the initial resistance to deformation, while the low carbon core maintained ductility. Because the core controls most of the tensile response, the overall tensile properties remained similar to normal milled steel, even though the surface was significantly stronger. Here, the goal was to confirm the increase in surface hardness caused by carburizing. The test was done using an indentation hardness machine. We placed the sample on the anvil, focused the indenter, and performed several measurements to ensure accuracy. As expected, the carburized layer showed a very high hardness compared to the core. This is due to carbon enrichment, which forms hard microstructures such as martensite and cementite at the surface. These results clearly show that carburizing improves wear resistance, but also makes the surface less ductile.
According to the microstructure analysis, the edge sample showed a clear case core gradient, which is typical of carburized steel. At the surface, we observe a high carbon microstructure with fine perlite and cementite, indicating a hardened case layer. In the transition zone, the microstructure gradually shifted to a mix of ferrite and coarser perlite as the carbon content decreased. At the core, the structure was mainly ferrite with coarse perlite colonies, reflecting the original low carbon steel composition. This confirms that carbon diffused inward during carburizing, creating a hard outer layer and a tough inner core. For section 5.2, the mechanical property analysis, the hardness results follow the microstructure. The surface shows very high hardness, typically between 550 and 650 HV. Due to the fine perlite and cementite, the transition zone has moderate hardness and the core is the softest. For tensile behavior, the core dominates, so the steel still behaves like mild steel with a yield strength around 250 megapascal and ultimate tensile strength of 400 to 450 megapascal and good ductility of 20 to 25%. The carburized layer mainly improves wear resistance and fatigue strength without significantly affecting overall tensile properties.
Okay, now I will explain how our finding relate to the client's complaint. First of all, our analysis showed that very clear link to the issue reported by the customer, which is the surface cracking during bending is consistent with extremely hard carburized case we have observed, which contains cementite network and also probably martensite. This make the surface brittle. Next, client also report inconsistent performance across the different plates, which match with our finding of non-uniform gradient, which suggests an uneven carburizing and leads to the unpredictable hardness and ductility. Some customers also face premature wear and surface damage. This is explained by the brittle cementite network that can form micro crack and cause surface spalling. Lastly, machining and welding difficulty are expected because the hardened surface increase tool wear and promote weld cracking. From the correlation that I mentioned before, we identified several root causes. The main cause is improper carburizing, where the plates were over-carburized or exposed to a carbon-rich environment for too long. We also found non-uniform carbon diffusion, likely due to the temperature or time inconsistency during the heat treatment. Other than that, we also found that poor cooling control may have introduced residuals to stress. And there might be some mismatch between the delivered steel condition and what customer need. Overall, all of these issues reflect a very weak supplier quality control. So, to solve all the problems that we mentioned before, we recommended clearer material specification in the purchase order, such as acceptable case depth and surface hardness. Plates, plates that are too hard should be rejected or normalized. Other than that, quality control should also be strengthened by hardness profiling, microstructure check, and regular supplier audits. This traceability system can help to track the plate quality. Finally, ABC Engineering itself should provide customer with the right material for their application, along with a proper machining, welding, and bending guidelines.
In conclusion, our analysis of the carburized steel showed that the surface was successfully hardened, but the process was not well controlled. The microstructure revealed excessive cement sheet and an inconsistent carbon gradient, which created a very brittle surface. This explains the clearance complaints such as cracking during forming, machining difficulties, and unpredictable performance. Overall, the study highlights the importance of proper heat treatment control and better quality assurance to ensure reliable and consistent steel properties.